Well, we've made it this far. One more finish out. The final will be Monday at 10:30. And as I said earlier, it's scheduled for 2 hours, or actually till 12:20, but typically students take about an hour to hour and a half on it. Some will take the full 2 hours, but most will take hour to hour and a half, kind of like the regular unit exams. There are 20 problems, so it will be about the same length as a regular unit exam. And we'll talk today what's the best way to study, what to concentrate on, what not to worry about. But essentially, the problems will be similar to the unit exams, but there's not going to be a lot from any one unit exam. There'll be a little bit from everything. So 20 problems. We had 5 unit exams. Now, I don't know that I cut it exactly equal. 4 from each unit exam. Well, maybe. Maybe it's 3 to 5 from each unit exam. We'll say that. So 3 to 5 from each unit. And today we'll kind of talk over what, or remind you what we covered, especially from the very beginning. That goes back a ways. Let's see. Best way to study for this is to look at your unit exams. Now, I do still have Unit 4 and Unit 5, Test 4 and Test 5. I need to hang on to those. Monday, I'll be able to give those to you. At least you can kind of look over what you had done wrong on those. But we'll talk through some of the problems there today. Those are recent enough that probably you will remember how to do those.
Is it alright if I...
Okay, on test 1, we looked a lot at limits. And in fact, first 9 problems was, here's a limit, find it if it exists. Now, at this point, we're just going to talk through the tests, and then as we have more time at the end of the class, we can go through certain problems. So if there's something that pops out and you think, oh, how did you do that? We'll work through those at the end of class as we have time. But there were several different approaches in finding the limit. First thing is plug the number in. If it turns out to be 0 divided by 0, then you've got some more work to do. And usually that means a lot of algebra. That darn algebra just gets to you everything we do. But some of it was factoring, some of it was the complex fractions, or fractions within fractions. Some was dealing with the square roots. Let's see, that was pretty much the 3 algebraic methods of kind of rewriting the limit. Then some parts of this we also looked at a graph. And there again, the idea, a limit means as x approaches a certain value, that means approaches from the right and from the left. If it approaches the same value, then that's the limit value. But if one side goes to, say, 1 and the other side goes to -2, then the limit does not exist. We do look at one-sided limits. If x approaches, or if the function approaches 1 from the right, okay, then if we have the x approaching some number and the little plus in the exponent position, that means x approaching from the right. That's the one side that we look at. But if there's no positive or negative up there, then it means from both sides. And if it does not approach the same number from both sides, then the limit does not exist. Also keep in mind, this is not the function value at that x value, but what's happening around, say, x equals 2. Okay. So keep in mind that, and then also the notation, refresh your memory on those. Then we also looked at where a function was not continuous, okay? And from a graphing standpoint, I'll just make up a graph here. Well, at this x value, we would say the function is not continuous. There's 3 different reasons a function would not be continuous. One, if the function value does not exist. Well, that's not the case in this graph, because f of whatever this x is would equal this point. Does this limit exist?
Yeah.
Okay, from the left, the y value is approaching this. From the right, the y value is approaching that same value. So the limit value exists. So whatever that y value would turn out to be is the limit value. This is not continuous because the limit value does not equal the function value. Here's the function value, here's the limit value. So basically a hole in the graph, we find the limit exists, possibly the function value exists, okay, but if there's a hole in it, then the limit will not equal the function value. Okay. So whether given a graph or maybe here's a function, show where we have discontinuity or where the function is not continuous. And then I did say where is it non-removable or where is it removable discontinuity. In this particular case, we would call this discontinuity what?
Removable.
Okay, that is removable, because if we simply replace the whole with one single point, then it would be continuous. But if it's non-removable, it might be something like this, where in this case the limit would not exist, because from one side it would come up here, the other side it would be here. We'd call that non-removable or jump discontinuity.
Can you have non-removable
So a lot of things to think about there: limits, function values, and then extending that to continuity. Some of our discontinuity problems, or where is the function not continuous. One was dealing with just a rational where you factor and something might cancel out. but a couple others were piecewise defined functions. And really the main problem there is where the two pieces connect, like the top piece goes, x could be less than 1, the bottom piece, x is greater than or equal to 1. Well, what we have to see is where do those two pieces connect? Is it going to be a situation like this, or do both sides approach the same value? And that's just going to be depending on the function itself. Figure out the one-sided limits, and that right there would determine whether it's going to be continuous at that point or not. Then the last part of test 1, we started looking at the ideas, the concepts leading up to the derivative, and position. Well, we've kind of done a little bit more with position now, and especially after this last test. In this unit, we had introduced the instantaneous velocity. Given the position, the derivative turned out to be the instantaneous velocity. Well, we know that forward and backward now, or at least hopefully we do. We should. But at least at that time, this was kind of new and different concepts for us. But we did introduce that. Slope of the tangent line, again, came from the derivative. Now, at that point, we didn't have the shortcuts, finding the derivative and so forth. We had to use the definition. But for those types of problems, if I say, here's the position function, find the velocity, just use the shortcuts on that. Now, that being said, one problem on test 1 also talked about use the definition of the derivative to find the derivative of a function. Yes, there will be a problem like that on the final. I will say, yes, there will be one for sure on that one. Okay. So the limits was the main concept here, but then towards the end of this unit, use the definition of the derivative so make sure you know what the definition of the derivative is and how to use it. That's the limit, does anybody remember, as delta x approaches 0, or some of you used h approaching 0, whichever, doesn't matter to me, of what?
Fx minus delta x.
Plus delta x, you're close. F of the quantity x plus delta x, then what? Minus, there's your minus, f of x, and then all over delta x. Okay. And once again, as with most of the calculus concepts, it's the algebra where we got a lot of algebra to do. Essentially, lots and lots of simplifying of the fraction here. Then finally, a tiny little bit of calculus at the end, and you get your derivative function. So yes, make sure you know how to do that, because you'll be asked that on one of the questions. So, okay, that was test 1. Now, again, as we have time, we can go back and look at specific problems, go over examples, but just to kind of remind yourself of what we've learned so far, or at least should have learned. Hopefully you still remember some of this. Test 2. Probably some of your favorite stuff, because we don't have to use the definition anymore. Test 2 was essentially a lot of the derivative rules, shortcuts, and you can be sure I'll have a few problems. Find the derivative of. Now, that could be using power rule, product rule, quotient rule, chain rule, all those different rules. And then we got into the trig derivatives. Okay, make sure you know the trig derivatives. Logarithms, the natural log, derivative of the natural log of x is
1 over x.
1 over x, okay. Now, sometimes life can be easier if you use the algebra, the log properties, to rewrite the logarithm before you take the derivative, but that's going to be a choice. I will accept it whether you use the log properties first or go directly to the really difficult derivative without simplifying it. But logs, exponential functions as well, e to the x or e to the 5x squared minus 3, something like that. Find your derivative. So lots and lots of derivative rules, trig functions, exponential, logarithmic derivatives. Another thing we looked at that kind of gave many of you some fits is implicit differentiation. So make sure you know how to do this. And we see this again, this idea again in test 3 with the related rates, like dx by dt, dy by dt, and those kind of things.
Are they going to be in word problems or just?
Possibly. A problem from test 2 would be basically, here's the equation, find dy by dx. So like,
Wait, can we get into that in test 3 then?
something like this, find dy by dx. Yeah, test 3 is where we got into the word problems. But problem for the final could be something like this, or possibly find the equation of the tangent line at some point. So 1, 2, or whatever point we're looking at. So there you got to look at the equation of a line as well. dy by dx would be your slope. Plug in the point x equals a, y equals b, and calculate the slope. Then use your point slope form or slope intercept form, whichever you prefer. Well, we looked at a little bit of that with implicit differentiation. Now, the last thing we looked at on test 2 was our position and velocity and acceleration. So, might have some, given the position, find velocity and acceleration. Whereas this last unit, we were given the acceleration, find the velocity and position. So hopefully that's still kind of fresh in your mind. And then the possible questions from that. In fact, number 20 out of test 2 deals with a rock through the air. what is the velocity when it hits the ground. So there, hits the ground means position equals 0. Solve that equation, that would give you the time it takes to hit the ground, and then plug that time into the velocity function to find the velocity when it hits the ground. Sounds kind of like a problem on test 5 too, huh? Except we were given different things on test 5. But a lot of similarities between this and what we looked at in test 5.
Except that one is forward and one is back.
Right. One, we start with acceleration and integrate to get to position. This one, given position, we differentiate to get to acceleration or to get to velocity. So questions about test 2? Now, test 3, I'm sure this was definitely everybody's favorite test, he said sarcastically. But lots and lots of different applications here. Test 3, we will kind of limit some of the possibilities. There will be no linear approximation on the final. So nothing like number 1. No Newton's method. So nothing like number 2. However, we do have some possibilities. 3 and 4, we're dealing with the optimization. So definitely possibilities there. Optimization. Given certain conditions, what will give us the maximum area, maximum volume, or given certain conditions, what would minimize the cost, minimize the surface area, minimize the distance, something like that. That was the optimization part. Then we got into related rates. And here on test 3, we had 2 cars leaving from the same point, one heading east, one heading north, and then how do we relate the distance between them at certain times. Or perhaps we have a ladder falling down a building. What's the rate that the base of that ladder is moving away from the building? Let's see, we had all kinds of different setups in the worksheets. Maybe a baseball diamond and runner going from second to third. How fast is his distance changing from home plate? So if you call that S, the baseball diamond, it'd be 90 feet between the bases, so call that X. All kinds of different types of problems that relate pretty much to a right triangle. You're probably going to have a right triangle problem on there. And of course, Pythagorean theorem would be the way you set it up. So there'll be a few application problems from this unit. Then we kind of felt like jumped to a totally different type of problem, but turns out to be very similar procedure, and that's working with the graphing functions. And with the graphs, we were finding maximum and minimum points, whether absolute maximum, absolute minimum, or relative maximum, relative minimum. For absolute, those could occur at critical points or at the endpoints of the interval. We would have a limited interval like from 0 to 3. Okay, so you check your critical points, but also check the endpoints on that. Relative or local maximums and minimums, those would just be where your critical points are. Possible maximum or minimum occur at critical points. Critical points also help us find where a function is increasing or decreasing. So be able to find intervals where certain functions increasing, where is it decreasing. And as we talked, the relative maximums and minimums. How do we find concavity?
Take second derivative.
Okay, second derivative deals with concavity. Concave up is where the second derivative would be positive. Concave down, second derivative would be negative. Whereas back here on the increasing and decreasing, it's first derivative. Increasing, first derivative is positive. Decreasing, first derivative is negative.
Do you like a cheat sheet?
No. You don't need a cheat sheet. You got the most important things in your head already. You know this. Then some of the concept problems may show up. However, nothing like number 10. I won't say here's a graph of y equals f primed of x. Okay. But possibly more like number 11.
Will we have to draw the graph?
Yeah, given certain conditions, f of negative 3 equals 0. Well, f of something means that particular point. Negative 3, 0 would be on the graph. F primed of negative 3 equals 0 would mean what?
It's at or that.
Okay, the critical point is at that point. The slope of the tangent line at negative 3 would be 0. So horizontal slope of the tangent line. And then possibly the second derivative of negative 3 is
Less than 0.
negative 5 or is less than 0. What would that tell us?
Concave down.
Okay, at that point the graph is going to be concave down. So possibly some problems like that where given different conditions, graph something that fit those conditions. Okay. And then the very last part of chapter or of test 3, vertical asymptotes and horizontal asymptotes. Make sure you know how to find those. In class, we did talk about oblique asymptotes or slant asymptotes, but there will not be anything like that on the final. But definitely find the vertical and horizontal asymptotes. Now, there you got to be careful because the vertical asymptotes, it's not necessarily where the denominator equals 0. We may have a hole in the graph at that point. So make sure you know how to find which is which. Okay. Questions on test 3? Okay, test 4. integration. We introduced the integral calculus. And we started off with the antiderivative techniques, or I guess we could say the antiderivative rules. There we go. Power rule, the trig functions. Make sure you know how to change the antiderivatives of trig functions. Well, that's kind of, you got to think backwards. Derivative of sine of x is cosine of x, so the antiderivative of cosine x would be sine x. So that you just got to think about and make sure you're going the right direction. Those can get a little confusing. And then one major technique we used in a lot of different ways is integrating by substitution. So make sure you know how to do that. And some of that would be to turn a real ugly antiderivative into a nice little, say, u to the third du. Well, that's a simple power rule, then resubstitute back. Or maybe 1 over u du, integrating that is the natural log of u. E to the u du, integrate e to the u and you get e to the u. Love that function. So, but sometimes getting the u and the du, that can be a little difficult. Now we looked at find the antiderivatives and a lot of the substitution, but also in here solve the differential equation. We saw that a little bit in test 4. Differential, too big a word there. Differential equation. We saw that also in test 5. So main thing there, starting with a first derivative or a second derivative, integrate, and then with the conditions we're given, we can find the plus c. C has to be 3 by the information given, or c might be -2, but be able to do that. We did look at some estimation problems. Estimate a definite integral. And some of you went ahead and found the exact value of that using the fundamental theorem. When I say estimate, I mean use your estimation. One part we led up to the definite integral using rectangles. And I'll probably limit this to 3 or 4 rectangles. And our sampling points, right or left endpoints to calculate the height of those rectangles. Okay. So make sure you're doing the correct side of that.
So it could be either or like you'll allow it to be either or.
I'll say and or. Maybe I'll say both. Use the right and the left to find 2 different estimates. So, question?
Yeah, you're not gonna have any.
Good question. No trapezoidal rule or Simpson's rule. So, trapezoidal or Simpson's. So no estimating using the trapezoidal or Simpson's rule. They would probably be some good problems for the final, but we have plenty of other finals or problems that are just as good or better. So. And that's actually the end of chapter 4, number 19 and 20. So don't worry about those. Also, you'll like this one. No definition of the definite integral. I figured I'd get loud cheers.
I think that's a little, no, you don't have to do that shit.
Yeah, careful. So, now, I did say earlier you would need to use the definition of the derivative. So we at least have one definition on there, but no definition of the definite integral. So don't worry about the limit as n approaches infinity of the summation of f of c sub I times delta x.
Yeah, see, I was gonna say that's a little, not biased, unfair to the other guys. I'm not complaining,
Yeah. Segregated.
Yeah.
Yeah.
Discriminative.
Yeah, discriminative. There we go. So nothing like that. Okay. However, fundamental theorem of calculus, definitely something like that. Part 1 or part 2. Now, part 2, most of you caught on real well on that one. Evaluating the definite integral, find your antiderivative, and then plug in f of b minus f of a, and that's the shortcut of your definite integral. But the part 1 was, instead of starting out with a definite integral and finding the value, we start out with the function, like number 10, function that looks like a definite integral, but we want to find the derivative of this.
That's what that one has. And put it in the right terms.
Well, the derivative of this turns out to be, well, the integrand, but we are in terms of x, so we need secant of 6x times tangent of 6x. Again, just an illustration showing the fundamental theorem, the derivative and the antiderivative are inverse operations. One cancels out the other one. Taking the derivative of an antiderivative, and we're left with just what was on the inside. But in terms of x, right, Yvonne?
Yep.
So.
Not team.
Okay. So let's see. Other things from test 4. Area, we began looking at area under a curve. Definitely extended that some for test 5. And I guess, and given a graph, number 18 on test 4, given a graph, evaluate a definite integral based on the area. Anything, when we're evaluating a definite integral based on a graph, any area that's under the x-axis represents a negative value for the definite integral. Any area above the x-axis represents a positive value for the definite integral. Now that's not to say these problems we were working with in Unit 5, we were only looking at area between curves, so we didn't have to worry about, well, that area is under the x-axis or above. We were setting those up top minus the bottom, minus took care of the area below the x-axis on there. So hopefully you can keep that straight. Okay, and finally, test 5, Of course, that should be real fresh in your mind, but to reiterate what we covered there, acceleration to velocity to position, and the different types of questions we had from there. Also solving a differential equation, which is exactly what we were doing in problems 1 and 2 on test 5. Acceleration represents the second derivative, and then we worked up from there. Vertical motion, problems 5 and 6, or no, 4 and 5. Again, acceleration and working your way up to position function. So that was kind of the first part of test 5. For the final, there will be no average value problem. Usually I hear a groan. That one. So, oh, you groaned, you just couldn't hear it. I just couldn't hear it. So no average value there, but then the last half of test 5 was the area between curves or region. I guess a bounded region would probably be the most general way to say that. Find the area between two curves, or under one curve and above another, or between the y-axis and a curve. Maybe it's x equals some function of y. So in that case, it's right minus the left. So. Okay, looks like we're at the end of time here. So any general questions? We will see you on Monday then.